So we're starting hypothesis testing, which is really probably the biggest thing we do in statistics. Okay, so we have confidence intervals is pretty big, hypothesis testing even bigger. So to introduce this, I have kind of a more practical example. So in another course, someone asked, how do we tell if a coin is fair? So what would your ideas be for how we could tell if a coin was fair? And so again, this is where we're going to start brainstorming. So what do you think we could do to tell if the coin was fair?
Like a zillion times and see if it's 50-50.
Okay, so we're going to flip it. I'm just going to say many times and see if we get 50% heads. Okay, sounds good to me. Now, just to make things a little bit easier on ourselves to do this brainstorming, let's say we're going to flip it 10 times. Not as accurate as doing it 1,000 or 1,000,000 or a zillion times, but just 10 because we can actually compute those probabilities. Now, if the coin is fair, how many times would you expect to get heads? 5, right? So let's pause and actually flip a coin. Actually, I don't want to do that. I'm going to write down what we did last time. It takes long to find my coin in my wallet. So last time I got heads, heads, tails, 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 head, tail, 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 head. Okay, so this one was 4 heads. So I didn't get the 5 that I was expecting. But even if the coin is exactly fair, or is fair, are you going to get exactly 5 out of 10 heads every time? Okay, no. You expect some variation. So sometimes I probably get it 4 times, and 5 times, and 6 times. Sometimes I might even get 3, or if it was a really, really unlikely chance, maybe I don't even get only like 1 or something. Okay. So now I'm going to ask you of how many heads do you think you could get in 10 tosses and still think the coin was fair? I'm not asking you for a statistical correct answer. But for you, if you were flipping a coin, how many heads do you think you could get and think the coin was fair? Okay.
37?
So Justin here is saying 7 to 8. You're saying 3 to 7. I like 3 to 7. That sounds good. Because if we're expecting 5, it kind of makes sense. You might get like 3 or 4, 6 or 7. Now, these are just kind of gut feelings. We're not doing anything too exact yet. Okay, so then that means if we got 3 to 7, we think the coin's fair. So that means first we think the coin is not fair, or we think the coin's not fair if I get 0, 1, 2, 8, 9, or 10. And so again, why did we pick these numbers? Did we have any mathematical reasoning? Not really, it was just kind of our gut feeling. Okay. But we did use our gut feeling, so we're going to go with it. So we're going to sit down and say, let's make a rule. So we will believe the coin is fair if we get 3 to 7 heads and 10 tosses. So which means that my coin, which I tossed and got 4 heads, we would think is fair. And we'll believe the coin is not fair if we get 0 to 2 or 8 to 10 heads and 10 tosses. So what we're going to do is we're going to flip an electronic coin. Okay. We don't know if the coin is fair or not, but the computer does because it knows what probability it's using. And we'll use our rule that we wrote to decide if the coin is fair, if we believe that the coin is fair. And keep in mind that we're dealing with probability, so while getting like 10 heads and 10 tosses on a fair coin might be very unlikely, it is still possible. Or getting 8 heads isn't as likely, but it's still possible. So we might not always be right. So what we'll do is we'll go through, we'll write the number of heads and 10 tosses that we get when we flip these coins. We'll write our decision, and then the truth, because the applicant knows if it's fair or not, and if our decision was correct. So we can toss the coin 10 times. We get 6 heads on this one. So for 6 heads, with our rule, we would think that the coin is fair, because we say it's fair from 3 to 0.7. But this one actually had a probability of 0.6 and the coin was not fair. But that kind of makes sense. A probability of 0.6, 6 heads would be quite likely. So let's go fill that in. So we had 6 heads. We believe that the coin is fair. The truth, though, is that it was not fair. So our decision was not correct. Let's get a new coin and try again. So we toss it, we get 5 heads. So we're going to believe the coin is fair, and it was. We like those results better. So 3, we think it's fair. The coin was fair, so it's correct. Okay. New coin, let's toss it 10 times. We got 5 heads again. I believe the coin is fair, but this time it was once again 0.6, so the coin was not fair. Wait, why did I write 3 there? Sorry, the last coin was a 5. You guys need to say something. Alright, stuff like that. So we think it's fair, but it was not fair. So we were not correct. New coin, let's toss it 10 times. Okay, I got 2 heads. So for 2 heads, what are we going to think? Not fair. And the coin was not fair. So 2, we think it's not fair. And the truth was that it was not fair. So we're good. And one more time. So we get 4. I would believe that it is fair. Oh, and the coin is not fair. We've gotten that 0.6 a lot of times tonight. That's unusual. So 4, we thought it was fair, but it was not fair. And so we were incorrect. Trying to get a fair coin. Oh, here's 0 heads. I probably think that one was not fair. Yep. Okay, so here's a 6. This one's probably fair, hopefully. No. So this one's a fair coin. I just want to kind of see what we're getting when we toss it. So we can keep tossing the same coin. So we get 6 heads, 5 heads, 4, 3. Look, even on this fair coin, we just got 1 head. So it's unlikely, but still possible. 3, 5, 7, 5, 4, 5, 6. So most of the time we are in that 3 to 7 range, but every once in a while you still kind of get one out of those bounds. So it is important to keep in mind that anytime you're dealing with probabilities, you might end up making mistakes. Even if you have a logical, very well balanced rule or a very well thought out rule, you might still make mistakes. And it's not even so much your mistakes, it's just that you get weird data. So what we'll do is we'll label some of our work. So first you have what's called a null hypothesis. This is your status quo, or the statement being tested, and in our case, status quo was that the coin is fair. Until we knew otherwise, we believed that the coin was fair. The alternative hypothesis is the opposite of the null hypothesis, so the coin is not fair. Then you'll always have some kind of test statistic. This is a number or a value computed from your sample data. In our case, we looked at the number of heads. And you'll have an acceptance region, which is the set of values of the test statistic that convinces us to believe the null hypothesis. So in our case, if we got 3 to 7 heads, then that led us to believe the coin is fair. And the rejection region of 0 to 2 or 8 to 10 heads leads us to believe the coin is not fair. Now, kind of going back, let's look at our logic again. So how did we pick our rule to decide if the coin was fair? So once again, this was just kind of our gut feeling, or we just pulled some numbers out of our head that sounded good. And this probably isn't the best way to make decisions, and another scientist might not necessarily want to believe our decisions. We're going to want to think of some mathematical or statistical way to approach making our decision rules, okay, or picking the acceptance and rejection regions so that other people will believe that we have some strong evidence. So let's look at what we know statistically. The number of heads we get in 10 coin tosses is a binomial distribution. Remember anything about the binomial distribution? Okay, now if we assume that the coin is fair, okay, this is the key word here is assume, because we always assume the null hypothesis is true. Because it's kind of our status quo, or what we believe until we know otherwise, so we always assume it's true for all of our calculations. So if you assume the coin is fair, then our probability is 0.5 and n equals 10. So for the number of heads, I have here the probability for each possible number of heads. So the most likely one is, of course, 5. 4 and 6 are pretty likely still at like 0.2. Even 3 and 7 are pretty likely at 11% chance. And then from there we said, okay, we didn't quite believe 2 because that was only 5% chance. 1 is only a 0.1% chance. And 0 is 0.9% and 0.1% chance. Okay, and also our nice little graph here. So you can see 3 to 7 are pretty likely, and 0 to 2 and 8 to 10 aren't very likely. So let's look at this. What is the probability that we will decide the coin is not fair in error with our first decision rule? So the coin really is fair, but we think it's not fair. So we said not fair if we got 0 to 2 or 8 to 10 heads. Okay, but if the coin really is fair, so the null hypothesis is true, then the probability of getting 0, 1, 2, 8, 9, or 10 heads is what? Okay, so let's come back up. Let's look at all these probabilities for the 0 to 2 and 8 to 10 heads and add them together. So 0.001 plus 0.0098 plus 0.0439 plus 0.0439 plus 0.0098 plus 0.001 equals 0.1094. So this means if the coin really is fair, we have about a 10% chance of deciding not fair. So if the coin is fair, we still have a 10.94% chance of deciding it is not fair. And then of course we would be incorrect. So when we do hypothesis tests, we want to go through and we want to make this probability of if the null is true, we want to make the probability of thinking that it's not true, we want to make that small. So what we're going to usually do is pick a decision rule that will ensure the probability that we make an error and decide that a fair coin is biased is less than 5%. So we want to change this probability from 10% to less than 5%. So which options are we going to have to take out? Okay, go ahead and guess.
2 and 8. Let's just
Okay, so you want to take out 2 and 8, and both of those are actually really close to 5% themselves, and so if we probably can't leave either one in and keep it less than 5%. So let's take out the 2 and 8, and double check. So probably the 0, 1, 9, or 10. Let's add those up: 0.001, 0.0098, 0.0098, and 0.0010 give me 0.0216. Can I add either the 2 or the 8 back in without putting it over 5%? Okay, no, so that's all we can do. So our new rule is we would say not fair if 0, 1, 9, or 10 heads. And what that will do for us is it makes the probability of taking a fair coin and deciding it's not fair down below 5%. So it reduces the probability of a specific error. So this probability that we just found here of 0.0216, that's going to be equal to what we call alpha. We call that alpha, or our significance level. This is also equal to the probability of a type 1 error. So a type 1 error is when you reject a true null hypothesis. So if you have a true null hypothesis, we don't want to reject it. And the probability of a type 1 error is equal to your alpha. Okay, so we made it so we only have a 2% chance of making a type 1 error. Unfortunately, it's not the only type of error that we can make. So here, when we reject a true null hypothesis, this means that the coin is fair because we have a true null, but we decide it is not fair. And a type 2 error is when we fail to reject a false null hypothesis, which would mean that the coin is not fair, but we decide it is fair. So if we come back up to the previous page, which type of error did we make? Because we made a few errors, didn't we, on our coins? So like my first error was the coin was really not fair, but we thought it was fair. So what type of error is that? Coin is not fair, but we think it's fair. That is a type 2 error. And in fact, all three that we did were that same situation. So we have a type 2 error. Now it turns out, so we can set alpha, and we can make alpha as small as we want, and that's the probability of a type 1 error. So we can control our type 1 errors, but we can't actually control the probability of a type 2 error. Because that's kind of if the coin is not fair, and there were a lot of different possible probabilities of heads that we could have gotten that had a not fair coin. And if you get a probability of a not fair coin where the probability of heads is like 0.6 or 0.4, you're going to get results pretty similar to a fair coin, and so you're going to make a lot of mistakes there. Okay, but you can control the probability of a type 1 error. Okay. Now I mentioned it's a significance level, so your level of significance is called alpha. And what this means is the evidence is considered to be strong enough to reject the null hypothesis if the data in our sample would only happen, well, 100, you just change it to a percentage, 100 alpha percentage of the time, or less when the null hypothesis is true. So in our case, if our coin is fair, we're only going to get evidence that will make us decide it's not fair 2.16% of the time. Because we figured it out, so we're only going to, if it's fair, we'll only get 0, 1s, 9s, or 10s and reject it 2% of the time. Now usually in statistics we'll choose a significance level of 0.05. That's our default, but you could also have 0.05 0.01 or 0.10. So most people use 0.05. More serious scientists, okay, and some of the more serious fields sometimes use 0.01 because they really don't want to make mistakes. And social sciences, they apparently don't think it cares quite as much, and they'll use 0.1. So what we're going to do is we've kind of worked through one example. We're going to do a similar thing, but with a six-sided die and trying to decide if a six-sided die is fair or not. So if a six-sided die is fair, how many times would we expect to get a 4 if we rolled it 10 times? Well, for a six-sided die, you'd have a 1/6 chance of getting a 4. And if you roll it 10 times, that would be 1.666 fours. Now, I just picked 4s because I just have to pick some number on the die. I could have said how many 3s would we get or how many 2s would we get, but let's just look at the 4s on the die. So now, if your die is fair, then let's let x be the number of 4s rolled on the die. Then that's going to have a binomial distribution. The probability of getting a 4 would be 1/6, and n would be 10. With a binomial distribution, then I can find all the x's and probabilities. So we have like a 16% chance of getting 0 4s, 32% chance of getting a 1 4, 29% chance of getting 2 4s, 15% chance of getting 3 4s, 5% chance of getting 4 of them, but only 1% chance of getting 5, and then it just keeps going down from there. So we want to use a significance level of 0.05. And let's start with labeling all of our pieces, or finding all of our pieces. So what would be the null hypothesis? You always start with status quo, and that's always going to be kind of the die is fair. Because most dice are assumed to be fair. Then the alternative would be that the die is not fair. So what would be our test statistic then? Remember, our test statistic is some number that you're computing from your sample data. And so what would be the natural thing to compute? It would be our number of 4s. So now we need to make a decision rule, but we want to have a significance level of 0.05. What that means is if it's fair, we want only a 5% chance of deciding it's not fair. So if it's fair, these are our probabilities. Let's start at the bottom and count up until we get to 5%. Now on the last problem, we did kind of both sides equally because my distribution looks symmetric. Is this distribution symmetric? No, and really like 0 hit 4s is pretty likely. So we'll start at the bottom and count up until we get to about 5%. We want to get as high as we can, but not go over. So if someone put this in your calculator, how high can we go without going over? Five. Okay. So let's find the probability that x equals 5, 6, 7, 8, 9, or 10. So adding them all together is 0.0155. So if I want to make sure I stay under the 5%, then we'll only want to reject if it's true for these numbers. So our acceptance region is we'll think it's fair if we get 0 to 4 4s. And we'll think it's not fair if we get 5 to 10 4s. So again, we picked this decision rule so that the probability of deciding it's not fair when it really is less than 5%. So what we're going to do now is go roll some different die, 10 times each. Okay, we'll write down our test statistic. The number 4 is our decision, whether or not we're rejecting or failing to reject the null hypothesis. The truth, if we made an error, and also we can write down what kind of error we made. And of course, every time I do this, I get different sets of results. So let's toss our coin, or our die. So this time I got 2 4s, and so 2 is in that 0 to 4 region. So I think it's fair, and yes, the die was fair. So let's go fill that out. So we got 2 4s. Our die is, or we believe it's fair. And so because we believe it's fair, what we're going to do is we're going to do what's called a fail to reject the null. Because our null is that it's fair, so we're not going to reject that. The truth is that it was fair, and so we didn't make an error. Go back, we'll get a new die, we'll toss our coin. Once again, we got 2 spots. I believe the die is fair, and it was fair. So go ahead and just do ditto marks on your next line, I guess. Okay, let's get a new die. I'm kind of bored with 2 spots. Okay, here's one with 9 spots, or 9 4s. So for 9 4s, our rule says that we should believe that our die is not fair. And in truth, the die is not fair. Good. Okay, so we got, or copied everything from up above there. And then our next one we had 9, so we believed it is not fair. And so because we believe it's not fair, we would reject the null. So remember, our null was that it was fair. So we'll reject it because we don't think it's fair. And the truth was that it was not fair. And so that was the correct decision. We didn't make an error. So new die, toss it. This time I got 0 spot, or 0 4s. 0 is in our fair region. Oh, but this one, actually, this one die isn't balanced at 1/6. It has a 0.05 probability of force. And this die is not fair. So we got a 0. So we thought it was fair, and we failed to reject. But in truth, the coin is not fair. So we did make an error. Now you guys have to figure out which type of error. This is a type 2 error. So the null was false. It was not a fair coin, but we thought that it was fair. Let's go see. Hopefully we can get another, or type 1 error so we can compare. Let's see. This one has 5 4s, and 5 to us says not fair. And this die was not fair. So fill that in. So 5 means not fair. And so if it's not fair, we would reject the null because we believe it's not fair, and in truth it was not fair. So we're doing good. And then I'll probably just keep doing dice until I can see a type 1. So here's 4 spots. I believe that it's fair. Oh, but it was not fair. So you guys can write that one down if you want. And keep going. That would actually once again be a type 2. The p-value is the probability of observing our test statistic or something more extreme if our null hypothesis is true. Okay. Now, when you read this, it sounds like a long, complicated interpretation, and people always ask me to simplify it, and you can't really simplify it. Okay. So the definition of the p-value always has 2 things. Sometimes I can reward it slightly, but basically it's telling you if the null is true, the p-value is the probability of getting our sample data or something more extreme. So it always has at least these three components. So if the null is true, it's a probability and it's of getting our sample data or something more extreme. So if you are looking through all of your homework, or especially on the exam, because these kinds of things are on the exam, and you see a definition that doesn't look this long and complicated, you know it's going to be false. And this is one of the most common misconceptions in statistics is people write down the wrong definition of a p-value, or they interpret it incorrectly. Okay, so it's truly, if the null is true, what's the probability of getting our sample data or something more extreme? Now, when we say more extreme, we mean our data set would give us kind of even more evidence against the null hypothesis. So extreme is always kind of against the null hypothesis, the unlikely things. So for example, if we rolled 5 4s, the p-value is the probability that we would roll 5 or more 4s with a fair die. Notice it's with a fair die because it's if our null hypothesis is true. And what we'll do is we report our p-values so that people can see how strong our evidence is and not just our conclusion. So up above we were just saying, oh, we think it's fair or not fair, but now we'll report our p-value and it kind of tells people how strong our evidence is. Okay, so from our previous page, we'll write down our test statistic for each of the die we wrote down, and then we'll write down the probability of observing that test statistic or an even greater value. Let's see if maybe I can get these two pages side by side so I can write down what they were. So we had a 229055. Two, 29055. We didn't get a very wide variety of test statistics, did we? Okay, so now our p-values is the probability of observing our test statistic or an even greater value. Again, the reason it's greater is those are the even more unlikely circumstances. So this one will be looking for the probability that x is at least 2. Now off to the side I made this nice little chart for us. So for each x value I have the probability that it's at least that number. So for x greater than or equal to 2, my p-value would be 0.5156. Let's skip the other two. Probability that x is at least 9 is less than 0.0001 because most softwares and certainly our tables stop keeping track at less than 1%. Or not 1%, 0.01%, I guess. Let's see, for 0, probability of getting a 0 or more is, well, 1. Those are the only choices. And for a 5, it looks like we're at 0.0155. So those were all of ours. Let's also write down what's the p-value if we roll 4 4s. So the probability that x was at least 4, because it's what you got and anything that's even more unlikely. That's why we're going greater. So for the 4, we're at 0.0698. And the p-value for 5 4s, x at least 5, is 0.0155. So what was our significance level? We said, you probably forgot because it's been a little while now, but we said alpha is 0.05. And what was our decision rule? If you remember, we decided it was fair, or kind of believe the null, if we got 0 to 4 4s. And we believed it was not fair, so we would reject the null. If we got 5 to 10 4s. Now, what do you notice here? At 4, which is the end of kind of our decision rule, we had a p-value of 0.0698. How does that compare to alpha? Bigger or smaller? It is bigger. Now at 5, which is the first number that we reject for, okay, now my p-value is suddenly less than alpha. Okay. So that's not coincidence. This is actually our rule that you're going to memorize and use for the rest of the class. So if our p-value is bigger than alpha, we will believe the null. Which we don't ever say believe, we'll actually say fail to reject the null. And if the p-value is less than alpha, we will reject the null. So that's something you're going to want to memorize. If you have a big p-value, you fail to reject the null hypothesis. If you have a small p-value, you reject the null hypothesis.